Well, I guess it is time to start. So, welcome to this session of the European Non-Associative Algebra Seminar. And today we have the talk by Marco Farinati, who will talk about, well, the title is not exactly the same as we received, but no, it's okay. He will talk about short SL2 structures on Lie algebras and superalgebras, I guess, and related Jordan tables. So please, whenever you like.
Okay, thank you very much for the introduction and the invitation. I'm very happy to talk about in this seminar, and I'm very happy that you contact me. Just I received the first time I received the email, I just looked, it wasn't spam or something strange, so I discovered this seminar because of your invitation, and I'm very glad and proud that you invite me. So this is work in collaboration with a postdoc, Gonzalo, and I make a disclaimer. I'm not coming from Jordan algebra, from Jordan world or non-associative world. I come from homological algebra, and this problem begins for us when studying cohomology of usual Lie algebras, and the general question is if the Lie algebra admits some extra structure like an action of SL2. Since we all know the representation theory of SL2, can we say something about the cohomology with trivial coefficients, with adjoint coefficients, and and I like very much the exterior algebra as coefficients. So that's the origin. And this postdoc made a lot of computation with the smallest Heisenberg Lie algebra. And it happens that for the three-dimensional Heisenberg Lie algebra, when you compute the cohomology with the coefficients in this exterior algebra, there are just a few representations that appears. That's the origin of the notion of short. That's just a few. So this is the talk. Okay, so I will begin with very basic definition, like what is an SL2 Lie algebra, and I will comment previous results and our contribution. Sorry, yeah. So the very first is a kind of classical, well, a very classical result from the times of Tits, that what happens if the SL2 action gives only the trivial representation and the adjoint representation. So Tits realized that from such a Lie algebra, one can find a Jordan algebra. And in some sense, what's called a Tits-construction, well, we can reconstruct in some way the Lie algebra from the Jordan one, okay? And well, there's this construction is very natural, but natural in the non-technical sense because it's not functorial. This can be solved, and this is the origin of the TAG construction or TAG construction for Tits, Allison and Gao, and that gives a functorial way of reconstructing, well, or constructing a Lie algebra from a Jordan. So the first part will be short in the sense that only the adjoint and the trivial appears, and these two construction. Then in the super world, things are more or less straightforward. We can say we add signs, causal signs, and we take care about them. And And also in the, well, we come back from the non-super case, there is the notion of not very short, that looks like, so maybe to add the adjoint and the trivial is too restrictive. What about the natural two-dimensional defining representation? So if this representation appears, we call short, okay? In this case, there's a Jordan algebra, but there is also a Jordan module and extra structure. Part of the extra structure is a triple product. That is Elduque and collaborators are the one that, so the people who know more about that here. So any question you can ask me. I can ask for help if I'm not sure. So, but our contribution is in two sides. From one part, we enlarge the construction to the short world and also to the super. So this tag construction depends only on the Jordan, but if also the other representation appear, there's a model that there wasn't a Tits-Construction for a Jordan algebra together with the Jordan module and on all that structure. And also we did both for this huge amount of data and in the super case. While doing that, we realized that there was some subtlety with the triple product. So Elduque and collaborators built this triple product from the Lie algebra with the short type representation, and well, we can try to write everything in terms of the Lie products and SL2 action and try to find a formula for the triple product. Okay, we did that. Okay, and when we try to reconstruct, there are, well, you will see at the end of the talk, there are 10 cases of brackets. We need to check some morphism, just very natural morphism was a Lie algebra morphism. And in these 10 cases, 9 of them were easily seen to be okay, or maybe long, but easy, okay? No surprises. And with the 10th, we couldn't do it. And finally, we realized that we can find for some big part of the data, we can slightly move this ternary product. And so there was another ternary product that worked. And so that's maybe that's the most important part I want to make advertisement that our contribution is maybe the most important part of the contribution is to find this new triple product that in terms of the Lie structure was actually easy. Okay, so let's begin. So SL2, we all know what is SL2, the 2x2 matrices, EFH, the standard notation, and notice that this notation shows that the two-dimensional representation. So that means the action of the generators in the two-dimensional representation, if we think of SL2 as an abstract algebra. So an algebra with an action of SL2 by derivation is called very short if only the adjoint representation and the trivial appears. That means this is an isomorphism of SL2 modules. Only adjoint representation and, well, assume J is finite dimensional, so we can completely split, and just these two. And in case this V, this two-dimensional natural representation appear in the decomposition, we call short. So very short is a special case of short, okay? And if Che happens to be a super Lie algebra, well, we don't care. The definition is the same. So an abstract algebra is called short if only the trivial, the highest weight 1 and highest weight 2 representation appears, and if the highest weight 1 is 0, well, it's very short. Okay. So the classical case, suppose Che is a usual Lie algebra, and well, there is a trivial part. The trivial part is where the SL2 as trivially, so it's necessarily the invariant, that is a sub-Lie algebra, acts on Che by inner derivations. So that's why we call D, because it's a kind of Lie algebra of derivation of Che. And in principle, this is several copies of SL2 we write as a tensor product of some multiplicity vector space. So if we use letters X, Y, Z for SL2, A, B, C for this vector space, and D for this part, well, just by SL2 linearity, means that the bracket of Che, because it's SL2 linear, using just the Gleb-Jordan decomposition, there's no much place. The bracket of two vectors of this form and this isomorphism, of course, well, that needs to give a map from SL2 times SL2 to SL2, and there's only the bracket up to a constant, and from SL2 times SL2 to the trivial, there is the killing form up to a constant. So necessarily the bracket is of this form. We use the standard bracket for SL2 and the killing form, and while this dot and bracket, there's just operations. So this dot goes from Che cross Che to Che, and so this formula is just, well, a bilinear map, okay? And here Tits realized that if Che is a Lie algebra, then this vector space, I'm saying Che and Che, okay? That's an English mistake of mine. Okay, sorry. So this vector space, together with the dot operation, is a Jordan algebra. Okay. And what can we do in the other side? So suppose now we have a Jordan algebra. Well, I recall what the Jordan algebra is. So the Jordan algebra is a vector space with a commutative operation, and this associativity works when this one is a square, okay? So this is not a bilinear equation or a trilinear equation like Jacobi, but we can also give a multilinear version that it's okay for that is most suitable for the super version, okay? And what Tits make is, beginning with the Jordan algebra, well, we need this extra derivation part. So we tensor with SL2, and we want this to be a Lie algebra. That is a kind of inverse construction. Well, we need to know what the inner derivation is. Suppose we know, we make the sum, and this define So we copy the formula from before. So now suppose this is well known, okay? So we have a Jordan product. So we define a bracket by this formula. And suppose D is some derivations, okay? And what is a derivation? Well, derivation is something that satisfies Leibniz rule. What is inner derivation? Well, it happens that from a Jordan algebra, if we compute that, of course, if the product is associative, this is 0. But it's a Jordan algebra, so it's not associative, this is non-zero. But using the Jordan identity, it happens that it is a derivation of the Jordan product. So this is by definition minor a, b, bigger, okay? So the bracket AB. So, well, what is nice, if we give an example of a nice Jordan algebra, then we have a nice Lie algebra. And Tits uses that in order to construct exceptional Lie algebras from the kind of small dimensional Jordan ones, okay? And well, there is some problem. The inner derivation is not functorial. So this is very natural, but not functorial. For example, suppose you have a really associative commutative algebra. Inner derivation are 0, but if this is inside a big one, so it's not 0 anymore. So it's not functorial. So, but there is a solution. This TKK is from Tits-Kantor-Koecher, and the Tits-Allison Gao construction is the following. So instead of AB between brackets, let's put some symbol, natural symbols on A and B. And we want this symbol to act as if it were that inner derivation. So it satisfies some relation, and so if you go back, this is symmetric. So this has to be symmetric, okay? Because this is symmetric. This is anti-symmetric. This has to be anti-symmetric. And so the first one is, well, A tensor B. The symbol AB has to be minus BA. So this is one obvious relation. And well, there is another one. And we construct all possible symbols subject to this relation. And this is the functorial substitute, okay? And well, this is the formula for the bracket. So this is just a symbol. Well, this is a concrete formula, okay? This is the Tits-Allison Gao construction. So what about the super case? Well, the super case is almost straightforward. So the formula is the same, but now this vector space is a super vector space, these two. And what we have is that this is a super Jordan algebra. And this is a super Lie algebra, which is the Lie algebra of invariants. So what is a super Jordan algebra? That was the multilinear formula for the Jordan identity. Well, this is, sorry for the length, but this is the same with Kosul sign, okay? So, and Shang recently compared to Tits, so work on that and he wanted to make things concrete, and one of the things that we took from him is the description in terms of a kind of intrinsic description of the Jordan structure. For example, in here, if elements are in here, this is the highest weight vectors of this representation. So we identify the Jordan, so this vector space as a sub-vector space of eigenspace with eigenvalue 2, okay? that one is eigenspace with eigenvalue 0 for H and also for the other generators. And under this isomorphism, he described the dot product using the bracket, and F, remember, is the standard 0, 0, 0, 1 matrix from SL2. So this is the standard generator of SL2. So we can write the dot operation of the Jordan algebra instead of in terms of the original bracket and the generator. Well, this is the signed version of the TAG construction. And in case we have a super Jordan algebra, we have the two possibilities to consider the inner derivation or the TAG construction, and this is a super Lie algebra, okay? And well, meanwhile, in the non-super world, suppose we have a short, not very short, but a short Lie algebra. So we have as SL2 module this representation. So the names here are X and Y are elements of SL2, A, B are elements of this J, M or N are elements of this big M, and small d from this small piece, okay? So this list of formula is not any hypothesis, it's just SL2 linearity. So we ask the bracket to be SL2 linear, and it needs to be of this form. So the first two is like before, and then this is the natural action of SL2 in V. Well, this is some operation that we should describe, but it's an operation from J tensor M into M. So that's why M becomes a chain module. And well, this is an internal operation in M. So what is here? Okay. And well, this is the determinant of the matrices with two vectors in here. And this symmetric product is from SL2 times SL2, sorry, from V tensor V into SL2, there is only one map up to constant. Okay, well, this is a formula if you want, but we can say that in this vector, we choose the normalization to give the highest weight vector, and then the other is we multiply by F several times and we deduce the other. Okay, this is just in here we choose the normalization and the rest is SL2 linearity. So a Lie algebra of this form has two vector space here, J and M, and several operations. The dot, an internal product on J, and this is work of Elduque and collaborators. This is a Jordan algebra. M has to be a module and some maps, okay? This bracket maps and this delta map. And there are several ways of making a description of that. So let me see here. In terms of, so here we begin with a short algebra, and then we have, well, one possibility is to have this amount of data, okay? And well, there is a triple product given by that formula, okay? Triple products, and that give the name of a ternary, Jordan ternary algebra or J ternary. What's a Jordan ternary algebra? It's a Jordan algebra, a module, a Jordan module, and a triple product, satisfying some some compatibility conditions. And well, if you begin with the Lie algebra and you define the triple product in that way, then it satisfies the following conditions. Here is the list. It is not very important, each one of them. But for me, the important thing that is these conditions are satisfied if you define the triple product in that way, okay? Ternary Jordan algebras were old, if you want. They were considered by Allison several years ago, and he construct Lie algebras from this setting, but not in the way we did. And well, the extension of the definition of a ternary Jordan to a super ternary, it's okay. Okay, so there's no problem. Now we have a super Jordan, a super model, and the definition is this one, but we have to add signs in case we sweep letters. For example, in the first one is okay, then here it should be the sign of -1 to the we switch a with m, -1 to the a times m, and so on. Okay, so the introducing cosine signs gives the notion of a ternary structure. But similar to the description of the Jordan product, now in case we have just J and D, we have only the dot. But now if we have M, so V is the highest weight representation of highest weight 1. So the eigenspace of eigenvalue 1 reconstruct M, and we can describe the operations in terms of the SL2 action. And here's the formula. So we have the dot, and also the Jordan model, and the star, okay? And also we have super derivations. So this is an inner derivation of the Lie algebra, but it acts on the space of eigenvectors, and similarly for that, okay? So the F, A, and B are chosen in such a way that when you compute the action of H here, if you put something of eigenvalue 2, then this is also an of eigenvalue 2, and so on, okay? So it acts on J and on M. And if we follow the definitions, we have a formula for the triple product. Okay, so here is the formula for the triple product. Okay, it looks a nice formula, but surprisingly, there's another formula, that one, that is also a triple product. Okay, so that was very surprising for us. At the beginning, we didn't look for that, and we tried always with, well, we took the previous work and we tried to define everything in terms of this triple product, and 90% works, okay? Because in the 10 equations, in the 10 conditions, 9 of them were okay, but one, and well, this is the main point of, well, one of the points of our contribution to find that one. And well, so maybe we should recall from from here, we have the dot, the bullet, the star, and this partial, okay? And we have this formula, so we can define the partial and have the triple product, or we can have the triple product and define the partial, okay? So that's the choice. So one possible choice is this package with the dot, the bullet, the star, and partial, or we don't give partial and we give the triple product, okay? So when we give the triple product is something compatible with dots, star, and bullet, okay? And there's no partial here, okay? So we can begin with these three operations and the triple and give partial, or from partial and so, okay? So if you move a little bit the triple product, you are moving partial, okay? But you keep the other as it were. So, okay. So with you give me a triple product, I give you a partial. And once I have a partial, I have inner derivations. Recall that with the dot, we have this bracket operation and also inner derivation on J. Now we have inner derivation on M. So here there are some formulas from the bracket in terms of the dot or the bullet, and partial in terms of the bullet, the star, and the triple product, okay? So given the dot and, the bullet and the star, okay, we can define everything up to here, okay? And if I give you the triple product, I can't completely determine this delta, okay? So with this kind of symbols, we can define the inner derivations. And those symbols are built with letters A, B, or MN. So now we consider J tensor J and also M tensor M. These are going to be abstract symbol, and we put all this relation. What are all those relations for? Well, they have to satisfy the properties of this derivation. And in this way, we generalize the tag construction for short, not just for very short. So so we have theorem. The first theorem is that if we define with the previous relation, this construction gives a Lie algebra. So where is give me a dot, a bullet, a star, and a triple product. So with dot, bullet, and star, I give you this operation. So give me the triple product, and I can complete the definition of partial, okay? So if you give me this ternary Jordan algebra, I can make this definition. And this happens to be a Lie algebra, and this is defined in such a way that this is a Lie algebra, so that the relations are made on purpose. And this Lie algebra acts both on J and on M in the way that we expect, okay? Notice here the dependence on the triple product. So this is the first theorem, this kind of structural theorem. This is a Lie algebra, and so this allows to define the tag version. And So the theorem B is we can use this Lie algebra in order to construct a super Lie algebra from a super ternary one with the bracket, the formula that they should be. Here D is in here. Here are list of abstract symbols on J tensor J or M tensor M. So this D could be, well, linear combination of these two types. Okay, so these are, when we compute brackets here, we have one possibility, bracket inside. Second possibility in these two. Third possibility in these two, but these are two types. So it is 3 and 4. Then you have 5, 6. So 1, 2, 3, 4, 3. So 4, 5, 6, 7, 8, 9. Well, there are several. Okay, so there are a lot of possibilities, but the triple product are just when we compute brackets inside here. So it's a very big list of cases when you compute the Lie brackets. But well, theorem B is that everything works for any ternary product. This is always a super Lie algebra. And here is a theorem that gives formula for the operations in terms of the original. So suppose we are not reconstructing. We have a Lie algebra, a super Lie algebra, with very few. So that is short. So only the trivial, the defining, and adjoint representation appears. So we can define the eigenspace of eigenvector 2, the eigenspace of eigenvector 1, and the well, this is an SL2 algebra, so we can make product, Lie brackets, and action of SL2. With those definitions, this is a ternary Jordan algebra. So we have examples of ternary Jordan algebra. So from Tits, we call the Tits functor, okay? So the Tits functor is given a super Lie algebra that is short. We define a ternary Jordan algebra. There is another functor that is, well, you can choose the old ternary product, okay? So we have two Tits functor. Well, we chose this one because this is better in the following sense. When we want to reconstruct with this, so I mean with this simple version of the ternary product, we have an adjoint result, okay? And in a very small Lie algebras, if you see SL3 as SL2 algebra, we check that in that example, the two version of the triple product. And when we reconstruct with the new one, we reconstruct SL2 times some abelian factors. But when we apply the TAG construction to the old one, we have two commuting copies of SL2. So we don't reconstruct anything really related to SL3. So this is the advertisement of the new one triple product. This is better for reconstructing. Okay, so both works for defining functors, but this one, from our point of view, is better in the sense that, well, it satisfies this adjointness result, and well, for me, an interpretation of that is that it reconstructs much better some original Lie structure than the other one. Okay, well, that's all. Thank you very much for your attention.
Thank you very much, Marco, for this interesting talk. And there is time now for questions. I saw on the chat that there was one question that was already answered by Ivan Kaigorodov. It was the reference to the paper by Allison of 1976.
Okay,
Yes, but it is already in the chat.
Okay,
So
here. And
yes,
we found these papers sometimes after, you begin with doing computation and then you say, oh, that was already done. But no. Here, from a ternary Lie algebra, he constructs a Lie algebra, but he begins to consider J, direct sum M, and some endomorphisms of that, preserving something and so on. So in the better case, you can relate with inner derivation and so, but there's no even Allison is on there. There are no tag construction for ternary before us. Okay, so the tag construction for the ternary version, that is okay, what is that? So this definition of BS of this Lie algebra is new. It's not on that old paper. Okay.
Okay, are there any other questions? I have one. Marco, could you please go to the place where you define the new triple product? Okay.
Yeah. From here, you don't see very easily that they are not the same, okay? Because you may wonder, what if we use Jacobi identity enough times? So we saw that and we
I was going
didn't
to
know
ask
that
about
they were different, okay? It's not trivial, but until we compute in SL3 example, we weren't sure they were the same or not, because when we wanted to prove that the adjoint theorem, we have some map that was the obvious one that should work in the other side to be a Lie algebra map. We have some equality to show, and we really thought that we weren't smart enough, that maybe we should keep on working on using Jacobi identity more times until or whatever. But they are not the same. They are not the same. If you begin with SL3 and you put SL2 inside and in the obvious way, and you decompose, then you have a short structure on SL3. You compute these two and give different formula. Okay, different formula.
But are they related by a scalar or something?
I don't know, but they are different, and they are very different in the sense that if you use this triple product to reconstruct from the ternary algebra associated to SL3, you get SL3 cross, I think, 2 or 3 abelian copies. And if you use that one, you have a Lie algebra with 2 commuting copies of SL2 that contains 2 commuting copies of SL2. So they are not just a change of way of looking at, they are really different. They are really different.
Yeah, and do you have the formulas that relate the triple products with the deltas and the star products? Yes.
Here.
Here is the one with the original definition. Okay. And with the new triple product?
So what is the data? So if I give you the dot, the star, the bullet, this one is in terms of the dot, okay? If I give you that one, then there's only one triple product, okay?
Yeah.
But if I give you the dot, the bullet, the start, and nothing else, I can define that one, but I cannot define that one. I need the, so there's here, okay. So in the first three ones, so if you compute the partial of mn applied to A, you can define in terms of the bullet and the star, okay? But so the triple product appears only here. The symbol of the modules applied to the modules. Here is the one where the triple product appear. So if you give only, so if you give only that part of the data, you have some freedom for the triple product. If you give partial, then there's no choice. Okay, so there's only one triple product. Okay, but from here you can fix a Jordan algebra and a module and a star, and there is a variety of triple product that are compatible with all that. Okay, so there's a variety of partials that you can define. That was surprising. We thought at the beginning that was a kind of one-to-one, so that is, but no, there's some freedom for the triple products. Okay, and the triple product appeared on just in a very tiny part of the bracket. Okay, that's why almost all the, so it appears in half part of the partial. So if you
this triple product, does it satisfy the last property of the JT6? Yes.
I don't know. I'm not familiar with that.
Yeah.
So it satisfies all that. Okay.
It satisfies all this.
Yeah.
Okay. Yes.
And you see, when we define the bracket, where is it? Okay, what is hidden here is in here. Depending on D is symbol of AB or MN.
Yeah.
And in here is applied to something in Che. So the triple product do not appear here, appear only here and in this case. Okay, so in half of the cases. So there's 2 here, 1 here, 3, 4, 5, 6. So everything here except half part of that, you don't see the triple product. So that's why for most of the computation, we didn't have problem with this, I know, standard, well, naive definitions, but we found a problem in here, okay? And likely we could solve. And we solved with the, in terms of the SL2 action, it was the simplest one, okay?
I see. Okay, are there any other question? Well, if not, let's thank the speaker again.
Okay, I thank to you.
And we continue, we resume in a week from now.
Okay.
Thank you very much for your talk.
Thank you.
Bye, everyone.